Number 1. The Kola Superdeep Borehole Microfossils. On the 24th of May, 1970, a team of Soviet geologists began drilling a hole near the town of Zapolyarny on the Kola Peninsula in the far northwest corner of the Soviet Union, a stone's throw from the Norwegian border. They were not looking for oil. They were trying to reach as deep into the crust of the earth as human engineering could push. The hole they made, designated SG-3, eventually reached a depth of 12,262 meters. That is more than 40,000 feet straight down, and it remains the deepest artificial point on the planet to this day. Picture the strangeness of it. At the bottom, this enormous hole is only about 23 centimeters across, roughly the width of a dinner plate, yet it plunges down more than 12 kilometers. And somewhere around 6,000 meters as the drill chewed through ancient rock, the scientists pulled up something that should not have survived. Fossilized plankton, microscopic single-celled marine organisms locked in stone that was nearly 2 billion years old. They counted around 24 distinct species, and instead of being crushed into unrecognizable smears, the microfossils were carbonized and intact, still carrying their original carbon and nitrogen, rather than being replaced by minerals. Think about what that means. 2 billion years ago, the rock holding those organisms sat at or near the surface, washed by an ancient sea. Then tectonic forces buried it kilometers deep, and there it waited, until a Soviet drill bit brought its dead back into the light. The lead figure behind the deep science was the geologist Yevgeny Kozlovsky, and his team kept finding things the textbooks said were impossible. Liquid water was circulating freely several kilometers down, where the crushing pressure was supposed to forbid it. The water, they reasoned, had been squeezed out of the minerals themselves. The deeper they went, the more the planet fought back. The expected boundary between granite and basalt, a feature geologists call the Conrad discontinuity, simply never appeared. The rock stayed granitic, fractured, and soaked in water, and the heat was merciless. At the bottom, the temperature reached about 180 degrees Celsius, nearly double what the engineers had predicted. At that temperature, the rock became plastic, flowing back into the hole like dough, sealing itself shut. The deepest rocks they recovered were Archean, around 2.7 billion years old. You may have heard the legend of the Well to Hell, a recording of screaming souls supposedly captured at the bottom. That is a debunked hoax. The truth is stranger and quieter. The hole was abandoned in the early 1990s when the Soviet Union collapsed and the funding vanished. The site was demolished by 2008, and today a single welded metal cap seals the deepest wound humanity has ever cut into the earth. The drill had reached only about a third of the way through the crust. The mantle stayed far out of reach, but it had dragged up the dead of the early Proterozoic, and that was only the beginning of what drilling would expose. Number 2. The Lusi Mud Volcano. If Kola was a deliberate scientific reach into deep time, our next story is the opposite. It is an accident that opened a wound the Earth has refused to close. On the 29th of May, 2006, in the Sidoarjo district of East Java, Indonesia, the ground began to bleed mud. The eruption broke out just meters from a gas exploration well called Banjarpanji 1, operated by the company Lapindo Brantas. What started as a trickle became a torrent. At its peak, the vent spewed up to 180,000 cubic meters of hot mud every single day. The mud did not stop. It buried at least a dozen villages across the Prong sub-district and drove roughly 40,000 people from their homes. The name locals gave it, Lusi, is a contraction of Lumpur Sidoarjo, meaning the mud of Sidoarjo, and the material pouring out of the earth was ancient. It came from a layer of overpressured marine clays from the Pleistocene, roughly 1,000 to 1,900 meters down, old seabed that had been sealed under pressure until the drilling gave it a path to the surface. Here is where the science splits into a genuine fight. One camp, led by the geologist Richard Davies of Durham University, argued that the drilling itself triggered the disaster. Their reasoning was that the borehole was not properly lined with protective casing, so when the drill hit a pressurized zone, fluid surged uncontrollably underground in what is called a blowout, fracturing a path to the surface. A rival camp pointed to a different culprit. Just 2 days earlier, on the 27th of May, a magnitude 6.3 earthquake had struck near Yogyakarta, about 250 kilometers away. They argued the quake reactivated a buried fault, and the eruption was natural. When petroleum geologists voted on the question at a conference in 2008, the majority favored the drilling explanation. But the debate never fully closed, and a third view emerged that may be the most interesting. The researcher Adriano Mazzini studied Lusi as a sediment-hosted geothermal system fed by a deep hydrothermal network connected to the nearby Arjuna-Welirang volcanic complex. That connection keeps the mud hot, near 100 degrees Celsius at the vent, which is why it behaves more like a living volcano than a simple leak. Engineers tried everything to stop it. In one desperate effort, they dropped chains of concrete balls into the vent, hoping to choke it. It failed. They built levees and dams to corral the mud into vast gray ponds so large they are visible from space. The central crater has since subsided several meters, sinking under its own weight. And the mud keeps dredging up microfossils and ancient organic material from those deep marine layers, occasionally venting methane that flickers and ignites. Lusi is now the largest mud volcano eruption in recorded history, both in volume and duration, and it may keep erupting for 20 or 30 years or more. We are watching a new geological feature being born in real time, built from a mistake that reached too deep. Number 3. The Bertha Rogers Hole and the Lake of Molten Sulfur. Travel now to Ouachita County, Oklahoma. And the year 1974. A company called Lone Star Producing drilled a gas well named the Bertha Rogers No. 1 into the Anadarko Basin, one of the deepest sedimentary basins in all of North America, filled with up to 40,000 feet of accumulated rock. The well reached a depth of 31,441 feet, which is 9,583 meters. For a brief window before the Kola hole surpassed it, the Bertha Rogers well was the deepest hole on Earth. It took about 502 days of grinding to get there, the drill string cutting through hundreds of millions of years of stacked Paleozoic sediment. Near the bottom, where the rock was incredibly hard and hot, the crew switched to a diamond bit, and the hole narrowed to just over 6 inches across. And then, at the very bottom, the drill struck something almost mythological. A pocket of molten elemental sulfur. Consider the conditions down there. The temperature at the bottom of the hole was around 246 degrees Celsius, which is 475 degrees Fahrenheit. Sulfur melts at about 115 degrees Celsius. So far below the surface, sealed in the dark, sat a reservoir of liquid sulfur, a subterranean lake of molten yellow rock. The drill bit pushed into it, and that was the end of the gamble. The molten sulfur damaged the equipment and made it impossible to deepen the hole any further. The well had reached toward the deepest point in America and hit a buried hell. Where does a lake of molten sulfur even come from? The leading explanation is a process called thermochemical sulfate reduction. Deep in a hydrocarbon basin, at high temperature, sulfate minerals react with hydrocarbons and break down, liberating elemental sulfur and toxic hydrogen sulfide gas. That hydrogen sulfide, with its rotten egg smell, is one of the lethal hazards that haunt these deep, sour gas zones. Some researchers have explored whether microbial processes contribute to sulfur deposits at shallower depths, but at the searing temperatures of the Bertha Rogers bottom, biology cannot survive, and the chemistry runs on heat alone. The well did produce some natural gas, but it was never the commercial triumph that its record-breaking depth had promised. It stands instead as a monument to how hostile the deep earth becomes, where the rock flows, the water hides in crystals, and the sulfur runs like water in a furnace. The Bertha Rogers hole, near the town of Elk City, remained the deepest hole in the United States for decades, a reminder that the planet guards its depths with heat and poison. Number 4. The Siljan Ring Borehole. In central Sweden lies a ring of low hills and lakes about 52 kilometers across. It is the Siljan Ring, the largest known meteorite impact crater in Europe, blasted into existence about 377 million years ago in the Devonian period. In the 1980s, this ancient scar became the testing ground for one of the most controversial ideas in all of Earth science, and the drill that probed it pulled up evidence that scientists are still arguing about. The idea belonged to a brilliant and combative astrophysicist named Thomas Gold. Gold championed what is called the abiogenic, or deep gas, theory of petroleum. The mainstream view, then and now, is that oil and gas form from buried biological matter, the remains of plankton and algae cooked under heat and pressure. Gold argued something radical. He believed that vast amounts of methane were rising from deep within the Earth, primordial gas with no biological origin at all, and that the fractured rock beneath an impact crater would be the perfect trap to catch it on its way up. So they drilled. The well, called Gravberg 1, began in 1986, funded in part by the Swedish State Power Board. It plunged about 6,800 meters straight into solid granite, which is extraordinary, because oil prospectors almost never drill into crystalline basement rock. There is normally nothing there to find. But the drill pulled up a strange black magnetite paste mixed with traces of oil. Gold pointed to it as vindication. About 80 barrels of oil were eventually recovered. His critics were unconvinced, and they had a strong case. The drilling mud used in the well contained diesel-based additives, so the oil, they argued, was simply contamination from the drilling itself. The magnetite, an iron oxide, could have come from the drilling process, or, more intriguingly, from microbes. This is where the story takes a turn that even Gold's opponents found fascinating. The magnetite and oil sludge hinted at the presence of a deep biosphere, living microbes thriving kilometers down inside the rock, feeding on chemistry rather than sunlight. Gold himself leaned into this, publishing a book in 1999 called The Deep Hot Biosphere, proposing that life saturates the crust far below our feet. A follow-up well, Stenberg 1, was drilled in the early 1990s, and it too failed to deliver commercial gas. The whole project ended in financial loss, and abiogenic oil remains a fringe idea rejected by mainstream petroleum geology, which holds firmly that economic hydrocarbons come from buried organic matter called kerosene. Yet, the Siljan gamble was not a total loss for science. The impact fracturing really had created deep porosity and genuine gas shows, proving the geology even where it failed the economics. And the deep biosphere that Gold imagined turned out to be partly real. Modern research has confirmed that microbial life lives kilometers deep in solid rock, an echo of his vision surfacing from one of the strangest holes ever drilled. Number 5. The Bayou Corne Sinkhole. On the 3rd of August 2012, the swamp near the small community of Bayou Corne in Assumption Parish, Louisiana, opened up and began to swallow itself. A sinkhole appeared above a buried geological structure called Napoleonville Salt Dome, and what unfolded over the following years was a slow-motion catastrophe drilled directly into deep time. To understand it, you have to go back to the Jurassic period between about 160 and 200 million years ago. At that time, the early Gulf of Mexico was a restricted, evaporating sea. It flooded and dried, over and over, leaving behind enormous beds of salt up to several kilometers thick. Geologists call this the Luan Salt. Salt is lighter than the rock around it, so over millions of years it flows slowly upward in towering columns called salt domes, a process known as diaporism. As these domes rise, they trap pockets of oil and gas against their flanks, which is exactly why they are so heavily drilled and mined. The Napoleonville Dome was being mined for salt by the Texas Brine Company, using a technique that dissolves the salt with injected water and pumps out the resulting brine, leaving a hollow cavern. The problem was that this cavern had been carved too close to the outer edge of the salt dome. The wall failed, the cavern breached, and the overlying rock and sediment began to collapse into it. On the surface, the dark water of the sinkhole spread and deepened, and whole cypress trees, still standing upright, slid down into it and vanished. The sinkhole eventually grew to more than 30 acres and reached hundreds of feet deep. As the ground collapsed, it released crude oil and natural gas that had been trapped in the rock for ages, and the methane bubbled up through the water. Worse, the gas migrated into the local aquifer and seeped beneath people's homes, creating a genuine explosion risk. Authorities ordered a mandatory evacuation of about 350 residents. The communities of Bayou Corne and Grand Bayou were emptied for years, and many people never came back. Seismic monitors picked up swarms of micro-earthquakes and underground tremors as the cavern shifted in the dark. This was an induced geohazard, a human mining operation triggering the collapse of ancient geology. The crude oil, the methane, and the brine that came pouring out were all remnants of deep-time marine environments, sealed away for over 100 million years, and then violently exposed. It was not the first disaster of its kind. In 1980, the Lake Peigneur catastrophe, also in Louisiana, occurred when a drill punctured a salt mine beneath a lake, and the entire lake drained into the earth. Texas Brine faced lawsuits and a class action settlement. and the Bayou Corne sinkhole slowly stabilized over the years, but the scar remains. A flooded crater where a swamp once stood, and a warning about what waits inside the salt. Number 6. The Zealandia Cores. Not everything a drill drags up is horror. Sometimes it is revelation on a scale that rewrites the map of the world. Beneath the southwest Pacific Ocean lies a landmass of about 4.9 million square kilometers, and roughly 94% of it is underwater. Its name is Zealandia, or Te Reo Maui, and in 2017, a team of scientists led by Nick Mortimer of the New Zealand research agency GNS Science argued that it deserves to be called Earth's eighth continent. For a long time, Zealandia was dismissed as a collection of scattered, drowned continental fragments. To prove it was a real coherent continent, scientists needed physical evidence from deep beneath the sea. That evidence came from the International Ocean Discovery Program, Expedition 364's sister project, Expedition 371, which drilled the Tasman Sea and Zealandia region in 2017 aboard the research ship JOIDES Resolution. The expedition was co-led by Gerald Dickens of Rice University and Rupert Sutherland of Victoria University of Wellington. At 6 sites, the drills bored hundreds of meters down into rock now buried a kilometer or more beneath the waves. And the cores they pulled up settled the argument. They were full of fossil pollen, spores, and the shells of shallow water organisms, proof that parts of Zealandia had once stood above sea level, hosting forests and coastlines before drowning. The fossils spanned roughly the last 70 million years, reaching back into the Paleocene and Eocene, and many of them were warm climate plankton, showing that the region had been far warmer around 40 to 50 million years ago. These microfossils worked like paleoaltimeters, tiny instruments recording the elevation of the rock when it formed. Some told of deep ocean, some of shallow seas, and some of dry land. By reading them in sequence, scientists reconstructed an astonishing history. Northern Zealandia had risen and fallen by hundreds, even thousands of meters, and the timing pointed to a single dramatic cause. Around 50 million years ago, the great chain of subduction zones we call the Pacific Ring of Fire was being born, and the birth of the nearby Tonga-Kermadec subduction zone wrenched the seafloor up and down. Zealandia's story begins even earlier, around 80 million years ago, when it rifted away from the supercontinent Gondwana. As it pulled apart, the continental crust thinned and stretched, which is the main reason most of it eventually sank below the ocean. Mortimer's team mapped its full extent using satellite gravity measurements, seafloor bathymetry, and dredged rock samples, and their landmark paper appeared in the journal GSA Today. The high points of this mostly drowned continent still poke above the surface as New Zealand and New Caledonia, an entire continent hidden under the Pacific confirmed by the contents of a drill core. Number 7. The Chicxulub Peak Ring Core. Now we come to perhaps the most literal example of a drill recovering a single day from deep time. The day the dinosaurs died. Off the coast of the Yucatan Peninsula in Mexico lies the buried Chicxulub impact crater, the scar left by the asteroid that struck the Earth about 66 million years ago and triggered the end Cretaceous mass extinction. In 2016, a joint expedition of the International Ocean Discovery Program and the International Continental Scientific Drilling Program, numbered 364, set out to drill straight into it. The expedition was co-led by Joanna Morgan of Imperial College London and Sean Gulick of the University of Texas at Austin. From a liftboat platform called the Myrtle, anchored in shallow Gulf water, they drilled down about 1,335 meters below the seafloor, aiming for a specific feature called the peak ring. A peak ring is a circle of mountains that forms inside the largest impact craters, and Chicxulub's is the only intact one on Earth that can be reached by drilling. What the cores revealed was almost beyond belief. They recovered granite continental basement rock that had been violently uplifted from about 10 kilometers deep to near the surface in a matter of minutes during the impact. This confirmed a model called dynamic collapse, the idea that during a giant impact, solid rock briefly behaves like a fluid, sloshing and rebounding before freezing back into stone. The cores showed shocked and shattered granite, then melt rock, then a chaotic breccia called suavite, stacked in sequence like pages of a book written in a single afternoon. The most haunting part was a section about 130 meters thick that recorded the first minutes to hours after the impact, In a 2019 study, Sean Gulick and his team reconstructed what they called the first day of the Cenozoic from this one interval. The upper layers held charcoal from wildfires and clear signs of the tsunami that surged back into the crater, flooding it with seawater on that very day. And there was a telling absence. The sulfur-rich rocks that should have been there were gone, vaporized and blasted into the upper atmosphere by the impact. That vaporized sulfur is thought to be the true killer. As sulfate aerosols, it spread around the globe and reflected sunlight away, plunging the planet into a years-long impact winter that collapsed food chains on land and sea. Yet even at ground zero, life proved astonishingly stubborn. The researcher Christopher Lowry studied the rock just above the impact layer and found that life recolonized the crater within years to a few thousand years, far faster than anyone expected. Tiny burrows and microfossils showed organisms returning to the most devastated place on Earth almost immediately. The crater itself is about 180 to 200 kilometers wide, carved by an impactor roughly 10 to 12 kilometers across, moving at tens of kilometers per second, and a drill brought its first day back to us. Number 8. Project Mohole. Long before any of these expeditions, there was a forgotten moonshot, an audacious Cold War dream to drill all the way through the crust and touch the mantle of the Earth itself. It was called Project Mohole, and its target was a boundary named the Mohorovičić discontinuity, the Moho, where the crust gives way to the mantle below. The boundary is named for the Croatian seismologist Andrija Mohorovičić, who first detected it in 1909 by studying how earthquake waves bent as they passed through the deep Earth. The project was managed by a group with the wonderfully odd name of the American Miscellaneous Society, and funded by the National Science Foundation. Its key insight was a clever shortcut. The continental crust is thick, but the oceanic crust is far thinner, so the fastest path to the mantle ran straight down through the deep ocean floor. In 1961, Phase 1 of the project began in about 3,500 meters of water off Guadalupe Island, Mexico. The drilling vessel was a converted barge called the Cus-1, and to keep it hovering precisely over a single spot in the deep open sea, engineers pioneered a technology called dynamic positioning, using motors to constantly counteract the wind and waves. The barge drilled 5 holes, the deepest reaching only about 183 meters below the seabed. But the cores pulled up basalt lying beneath a layer of Miocene-age sediment, marking the first time scientists had ever cored the basement rock of the ocean floor. The famous novelist John Steinbeck came aboard to watch and wrote about the drilling for Life magazine. Then it all fell apart. The project never came close to the mantle, which beneath the ocean still lies 5 to 10 kilometers down, far deeper than Mohole reached. Costs ballooned from tens of millions of dollars toward more than 100 million, and amid bitter fights over management and budget, Congress canceled the whole effort in 1966. On the surface, it looked like a humiliating failure, but Mohole's true legacy was enormous. The dynamic positioning technology it pioneered became foundational for all later deep-sea drilling and for the entire offshore oil industry. And its failure directly inspired a more modest to wildly successful successor, the deep-sea drilling project, which began in 1968 with the famous ship Glomar Challenger. That project and the ocean drilling program and international ocean discovery program that followed it descend in a straight line from Mohole's ambition. They are the very programs that drilled Zealandia and Chicxulub. Reaching the mantle remains unaccomplished even now, with Japan's giant drilling ship Chikyu still pursuing the dream. Mohole overreached and fell short, but in doing so it built the tools that let us drag the rest of deep time to the surface. Number 9. The North Sea chalk and Ekofisk's Coccolithophore graveyard. Here's a quieter horror, one of pure scale. In 1969, Phillips Petroleum discovered a giant oil field beneath the Norwegian North Sea and named it Ekofisk. It was one of the first major North Sea finds, and it launched Norway into its oil era. But to understand what they were really pumping out of the ground, you have to look at the reservoir rock under a microscope. The reservoir is part of the chalk group, made of formations called the Ekofisk and Tor, deposited in the late Cretaceous and early Paleocene, somewhere north of 60 to 70 million years ago. And chalk is not ordinary stone. It is composed almost entirely of coccoliths, microscopic plates of calcium carbonate shed by single-celled algae called Coccolithophores. Over millions of years, trillions upon trillions of these tiny organisms lived, died, and rained down to the seafloor, building layer after layer of their own skeletal remains. The same chalk forms the white cliffs of Dover. The oil field, in other words, is a compressed mass grave of Cretaceous plankton, and the crude is pumped straight through the bones of the dead. But the dead did not rest quietly. Chalk is extraordinarily porous, holding up to about 40% empty space, which makes it a superb reservoir, but also mechanically weak. As Phillips and its partners pumped oil and gas out, the pressure in the reservoir dropped, and the porous chalk began to compact under the weight of everything above it. The seabed itself started to sink. By the mid-1980s, the Ekofisk platforms had subsided several meters, and the seafloor would eventually sink by around 9 meters. This created an engineering emergency. In 1987, in a staggering operation, the operators physically jacked up the platforms by about 6 meters to keep them above the rising waves. A protective barrier was built, and eventually the entire field had to be redeveloped in a project called Ekofisk 2. Total subsidence is projected to approach or even exceed 10 meters over the field's life. To make matters more complex, water injected into the reservoir to maintain pressure paradoxically weakened the chalk further in places, a phenomenon called water weakening. The story ties the microscopic dead of deep time directly to the sinking steel of modern industry. Coccolithophores are not extinct relics. They remain among the most abundant phytoplankton in today's oceans, turning the sea milky turquoise in swirls visible from orbit, the living source of the chalk of the future. At Ekofisk, humanity reached into a Cretaceous graveyard, withdrew billions of barrels of oil equivalent, and reactivated the ancient sediment, pulling the very floor of the sea down behind it. Number 10. The Ghawar Field. We end on familiar ground made strange. In eastern Saudi Arabia lies Ghawar, the largest conventional oil field ever discovered in the history of the world. Aramco founded in 1948, and it was on production by 1951. It stretches about 280 kilometers long and 30 kilometers wide, an immense arch of rock called an anticline that traps oil on a scale almost impossible to imagine, and every barrel of it is the liquefied remains of a vanished sea. The main reservoir is a rock called the Arab D limestone, and it was laid down in the late Jurassic period, roughly 150 to 160 million years ago. Picture the Arabian region back then. It was a warm, shallow, oxygen-poor carbonate sea, the kind of stagnant lagoon where dead plankton and marine microorganisms settle into the mud faster than they can rot. Those organisms, accumulated in vast quantities, were buried, and over geologic time were cooked by heat and pressure into oil. The source rocks include the organic-rich Jurassic Hanifa Formation, and the oil they generated migrated upward and collected in the Arab D limestone. What sealed it in place for over 100 million years is a cap of anhydrite, an evaporate rock, the dried residue of that ancient sea. And the great trapping arch was shaped in part by the slow movement of an even older salt, the Hormuz salt, dating back to the late Precambrian and Cambrian. So the whole structure is a layered monument to deep time, ancient salt below, Jurassic graveyard in the middle, evaporate lid on top. The numbers are staggering. Ghawar has produced more oil than any other field in history, cumulative output running into the tens of billions of barrels. At its peak, it produced around 5 million barrels per day, a substantial fraction of the entire planet's supply. The field is divided into areas with names like Ain Dar, Shedgum, Uthmania, Hawiya, and Harad, and keeping the oil flowing requires water injection to maintain pressure, horizontal wells, and constant monitoring of the water table rising inside the reservoir. The true remaining reserves and decline rates are guarded as state secrets, which is exactly why Ghawar sits at the center of every debate about peak oil. But strip away the geopolitics and Ghawar is the ultimate recognition anchor for this entire story. Every time a well draws oil from it, civilization is making a withdrawal from deep time's bank of dead life. The carbonate reservoir rock is itself built from the skeletal debris of ancient marine organisms. The fuel that powers the modern world is quite literally a Mesozoic sea that died, settled, and was buried, waiting 150 million years for a drill bit to bring it back. Step back from the individual holes, and a single thread runs through nearly all of them. Heat and pressure. The Earth gets hotter as you descend, on average about 25 to 30 degrees Celsius for every kilometer, a number called the geothermal gradient. But in deep sedimentary basins, it can run hotter, which is why Kola hit 180 degrees and the Bertha Rogers well reached 246 degrees Celsius near the bottom. Pressure climbs just as relentlessly, roughly 1 atmosphere for every 10 meters of overlying rock, until the stone itself stops behaving like a brittle solid. That is the secret behind Kola's strangest problem. Past a certain depth in what geologists call the brittle to ductile transition zone, hot rock under immense pressure becomes plastic, flowing slowly like putty. It oozed back into the borehole and sealed it shut again and again. To fight conditions like these, engineers reach for diamond-tipped bits, specially weighted drilling muds, and tools rated for extreme temperature, and even then, the planet wins more often than not. Add in the lethal hydrogen sulfide of sour gas zones and the molten sulfur of the deep Anadarko Basin, and you begin to see why the deepest holes ever drilled still barely scratch the surface. This is the humbling truth that links Kola, Bertha Rogers, and Mohole. None of them came anywhere near the mantle, which begins 5 kilometers down beneath the thinnest ocean floor and tens of kilometers down beneath the continents. Almost everything we know about the deep interior comes not from drills, but from seismology, from reading how earthquake waves bend and slow as they pass through the planet. Drilling is brutally expensive, with cost rising steeply as depth and temperature climb, and at some point the economics simply forbid going deeper. The dream of touching the mantle keeps colliding with the physics of the deep. There is a second thread, just as important, running through Bayou, Corne, Ekofisk, and Ghawar. Oil and gas are not merely fuel. They are archives of deep time, the bodies of ancient life turned to stone and liquid. Oil forms when buried plankton and algae are cooked within a narrow temperature band called the oil window, roughly 60 to 120 degrees Celsius. The waxy precursor material called kerosene slowly matures into oil and then gas over millions of years. Push the source rock too deep and too hot, and you get only gas, the organic matter cracked down to its simplest form. Every reservoir, then, is a record of a vanished ecosystem. The Coccolith chalk of Ekofisk and the carbonate limestone of Ghawar are bodies turned directly into rock, the skeletons of countless organisms compressed into stone. Geologists can even extract molecules called biomarkers from crude oil, chemical fingerprints that identify the specific ancient organisms that produced it. The microfossils trapped in reservoir rock let scientists date and correlate the layers, reading the age of the oil from the creatures buried alongside it. And the salt seals that lock these deposits in place, the anhydrite over Ghawar and the Luan salt of Bayou Corne, are themselves deep time signatures, the dried remains of evaporated seas. There's a quiet paradox in all of it. The carbon in fuel is ancient sunlight, captured by phytoplankton that died and sank during the age of dinosaurs and beyond. We are taking energy the Earth saved across tens of millions of years and releasing it in mere decades. The same mass burials of organic matter that produce these fields are often linked to oceanic anoxic events, episodes when the seas turned oxygen poor and life smothered in vast numbers. The oil is the legacy of those catastrophes, the dead of deep time fueling the living present. The strangest threat of all is biological. Again and again, drilling has dragged up not just dead rock, but evidence of life. Some ancient, some startlingly current. Kola pulled up plankton microfossils 2 billion years old, still carbonized and intact. Lusi and the Zealandia Cores brought fossil pollen, spores, and shells from buried marine and coastal worlds. The Chicxulub cores revealed life recolonizing the most devastated place on the planet within years to a few thousand years of the impact that ended the dinosaurs. And then there is the question Thomas Gold raised at Siljan, the one that seemed like fringe nonsense and turned out to be partly true. Is there life down there now, living inside the solid rock? The magnetite and oil sludge from the Gravberg well hinted at microbes living kilometers deep, and modern research has confirmed it beyond doubt. The deep subsurface is inhabited by Coccolithophores, organisms that live not on sunlight but on the chemical energy of the rock itself. Some estimates suggest this deep biosphere may rival the total biomass of everything living on the surface. These are not fast-living creatures. Some of these microbes have metabolism so slow that a single generation may span thousands of years, an almost geological pace of life. This is why drilling is such a double-edged tool. It reveals the deep biosphere, but it also contaminates it, carrying surface microbes and drilling fluids down into pristine rock, and making it maddeningly hard to know what was truly there before the bit arrived. And at these depths, the very line between fossil and living organism begins to blur. An organism dormant for tens of thousands of years, barely metabolizing, sealed in rock, sits in a strange gray zone between life and stone. The boreholes that connect Kola, Siljan, Zealandia, and Chicxulub all touch this hidden frontier, a biosphere we are only beginning to map. A darker pattern connects Lusi, Bayou, Corne, and Ekofisk, and sometimes the drill does not just reveal the deep past, it unleashes it. Lusi began as a gas well and opened a mud volcano that has buried villages and erupted for years. Bayou Corne began as a brine cavern and ended as a sinkhole that swallowed a swamp. Both followed an older precedent, the 1980 Lake Penieur disaster, in which a misplaced drill punctured a salt mine beneath a Louisiana lake and the entire lake roared down into the earth, taking barges and acres of land with it. Even Ekofisk, with its slow 9-meter subsidence, is a kind of sanctioned catastrophe, a seabed pulled down across decades by the steady withdrawal of oil. Across the industry, the injection and extraction of fluids can trigger induced seismicity, small and sometimes not so small earthquakes set off by human activity. Blowouts where pressurized fluids surge uncontrollably up a borehole are the nightmare that well control engineering exists to prevent, fought with heavy drilling mud, steel casing, and constant vigilance against the sudden pressure surge called a kick. The lesson echoing through all of these stories is the same. Deep time stays stable until we open a path to the surface. Overpressured fluids, trapped gases, and dissolving salt sit in equilibrium for millions of years, and then a borehole gives them somewhere to go. The fierce debate over whether Lusi was triggered by drilling or by a distant earthquake captures the uncertainty perfectly. In hindsight, investigators often blame inadequate casing or a cavern carved too close to a salt dome's edge, but the deeper truth is that we are puncturing systems we do not fully understand, and occasionally they answer back with catastrophe. Pull all of these threads together, and the picture that emerges is humbling. Every deep hole humanity has ever drilled is a core sample through time, a needle pushed into millions or even billions of years of stacked history. Kola read 2 billion years of crust. Chicxulub captured a single catastrophic day. Ghawar and Ekofisk drew up the liquefied and compressed dead of vanished seas. And through it all, the mantle, the vast hot heart of our own planet, has remained completely untouched, our greatest unreached frontier sitting just a few kilometers beneath the deepest hole we have ever made. That gap between ambition and reach is the quiet drama of deep drilling. Seismology gives us a blurred portrait of the interior, while drilling gives us a single vivid pinprick of ground truth. And we are forever trying to reconcile the two. Japan's drilling ship Chikyu still chases the dream that Project Mohole began more than 60 years ago, hoping to one day pull up a piece of the mantle itself. Some questions the cores have settled for good. Zealandia is real. The Chicxulub peak ring formed by rock flowing like a fluid. Other questions, like the true extent of abiogenic gas, remain stubbornly open. And there is a deeper tension underneath everything. We drill for fuel and we drill for knowledge. In the same chalk, salt, and limestone that warm our homes and move our machines are also the tombstones of deep time. The Coccolithophores of Ekofisk, the Jurassic plankton of Ghawar, the 2 billion-year-old cells of Kola, all of them are the dead being summoned back into the light. The deep biosphere reminds us that the boundary between the living and the buried is not as sharp as we assumed. The ground beneath your feet is not inert. It is a layered archive of heat and death and stubborn life and sudden catastrophe. And every drill bit that bites into it is a thin, fragile needle dropped into deep time, pulling up things we were never meant to see.